So let's take a look on the performance. We can look at the figure 3 that I show in the left-hand side. This data reveal the critical engineering um, reality. So once the metric dimension exceed 512, the on-chip NPU execution time increase exponentially. The technical reason is the capacity mismatch. The working set of the operation exceed the physical SRM capacity. Be precise, is only 2 MB for this Intel NPU. So when the internal room is full, the SRM, the system is forced to fetch data from much slower external memory, so causing the compute unit to wait while for the logistic. So here's come to my first concern. Um, the papers claim regarding the low latency inference are over optimistic because they ignore the cultivating engineering cost of the model swapping and its hidden logistics. Because the SRAM cells utilize a complex 6 transistor architecture, which is occupy significant silicon area, making the capacity of the 2MB constraint for the CPU. But in the real world, the concurrent DBMS multiple queries frequently require different ML model. This forces a constant cycle of loading and unloading data into this tiny buffer, which introduced two critical bottleneck the author failed to quantify. So first, that is Huon mentioned in 2019, the left downside, the NEU-MNU study. Frequently swapping is not just a data moving issue. It includes the heavy hover overhead in address translation. When processing the complex database table that store non-contiguously in the memory. So the MPU's address translation units become a bottleneck, adding a hidden latency before computation even begin. So second, we must consider the physical cost of the data formatting, as proven earlier in the Hugh in 2022 in the TCU-DB research. Relational data must be rearranging into the binary indicator tensor. So to be compatible with the NPU matrix multiply accumulator unit, where is the computer format. This table to tensor transformation also involve complex memory transportations and relayout operation. So it proved the two facts that the address translation overhead and data reshaping work will create this logistic cost that is likely to exceed the NPU actual computation time in high load engineering environment. So these overheads will negate the 1 nanosecond SS benefit of the SRAM. So that's the first thing I want to talk about. And second is that the NPU relies on the DMA, the direct memory access engine, to stream data from memory to the SRAM. So according to the Bestrow paper in 2024, the left-hand side conclusion, the synchronized data transfer via the accelerator like DSA, DMA are not free. They create the interference with the CPU side data intensive tasks. Um, the evidence shows that when both the accelerator and the CPU compete for the memory control bandwidth, the throughput of the both drops significantly. So it proves that the opportunity aforementioned in the database ML The seamless moving data is an idealization that fails under the high-low engineering condition. So, in conclusion, so when the system process in the high frequency data, the DMA directly competes with the CPU for the memory controller bandwidth. This bus contention create the I/O congestion, so it will slow down the speed. So here's comes to this solution. So to address those bottleneck, uh, I think the predictive logistics system, instead of the reactive loading, we should implement of the data flow based on this ODD, on the flight data distributions. So according to the Beerthroat in the 2024, using accelerator to synchronize distributed the data into the faster memory tiers during the query execution can improve performance by 18%, so that we could utilize the CPU to predict the next required feature set and drive the DMA to preload the 2 MB SRAM buffer. So while the NPU is still calculating the current blocks, effectively helps on the logistic latency. So next is the implementations on the HET path. So that's in the paper in the opportunity 7. The approach is to route the micro tasks and the small input to the iGPU. So taking advantage of its near data, near zero startup cost. So conversely, the large-scale matrix operations and the complex neural network feature extraction must be offloaded to the NPU, so which is specifically engineered for high throughput compute dense workloads. So final is the revealed thoughts. Uh, Based on my interest in the edge computing, the on-chips NPUs are perfect for the sub-millisecond anomaly detection, such as this sensor streams, while the low power and low latency are more important than the massive throughput. However, for the large-scale analysis, we must resolve the physical SRAM capacity and the bus contention problem that I have discussed today. So by analyzing the data logistic and the physical space constraint, we can fully understand how to leverage the MPU advantage. That's all my sharing. Thank you.